of the power consumption of the chip. And based on the power consumption, we'll know what we can do or should do to distribute the power from the I/O areas to other cells in the core areas. You guys see my cursor, right? Dave, Lou.
Yeah, we can see.
Okay, yeah. All right. So the purpose is providing power to our cells, right? And because the cells are the standard cells, the macros, they are like robots. They need power before they can move around. Without power, they cannot do anything. So we need to route the power from the path. The power comes from the outside. Sometimes if you have a PLL on-chip phase lock loop that generate the clocks and the power that generate the I got mixed up on-chip regulator, then the power can come from on chip. So the one of the purposes is to minimize IR drops. So you see why IR drop minimization is something that we need to pay attention to. Give me a minute. Sorry, I have to close the door. So you need to minimize IR drop. There are maximum IR drop constraints that due to the time enclosure constraints that we'll learn a little bit why we need to be concerned about IR drops. And then we need to minimize the self-heating for EM purposes. We'll see what they are about. And then last but not least, we want to be accurate. By being accurate, then we can avoid over-designing of the power grid. So if we do too much over design, then you will take away the routing resources, and also you will make the chip bigger, and so therefore more expensive. So you want to be you want to avoid over designing, right? So the power grid, how it is created and analyzed, a lot of things depend on the power consumption. So this is just a little bit review of what power means in electronic circuits, VLSI. So let's see. So this is a review. So as you know, right, power is current times voltage, right? And the if there's a resistor, then power dissipation, power consumption is I times S squared times R. The power is equal to V squared over R. So it's I squared R. So this is power dissipation through a resistor. And the energy that is needed to charge a capacitor is in integration of I VT dt or C dVdt VT dt. And then after you take the integration over the voltage charge on, you need to charge a VC on the capacitor. Then the charge stored here is equal to 1/2 of the C, which is the capacitor here, times the square of the voltage that you charge up. So that's the basic power. And then this is a little bit more detail about the charging of a capacitor. So if you have an inverter here, you have an output load. So energy stored in a capacitor, like we mentioned over there, is 1/2 of a C load times VDD square, because you charging on your circuit, VDD is charged, V out becomes VDD. So that's energy stored here. but the energy drawn from the power supply is something else as well. So as you go through the equations, and you will see CL times VDD square. So it's twice as much. So because half of the energy is dissipated, through this PMOS, right? So the other half is stored here. So likewise, if you discharge the CL when V out goes from 1 to 0, then you go through the N transistor. So the energy is dumped into ground. So half of CL VDD square is dumped, and half of it is dissipated in this N transistor as heat. These are dissipation as heat. Okay. Um, so these energy affects battery, but you learn later on. Okay, so the sources for power dissipation are the total of a power is a dynamic plus static. So for dynamic, you have switching and short circuit. So we can go over this a little bit later. I hope I have pictures. But the switching is when you have this operation, when you go from Vn going from 1 to 0, you're charging this capacitor, and V out it goes from 0 to 1. You're switching. So that's a switching current. But as Vn goes up, um, I cannot draw because I'm zooming in. But if Vn goes up and it slowly going up, then when Vn passes the threshold of these two, then there's short circuit current that go from VDD to ground. That part is part of the dynamic power when you switch. But the static power is really there is a consumption when there's no activities, no operations on the circuit. So it involves VDD times the current, the substrate current, the gate current, the gate that goes through current. If you look at the three the cross section, then the substrate will have some current. The gate will have some current through the gate oxide. The junction, the N plus and P plus have leakages on that junction. And there's something called contention, meaning that if you have two gates driving one load and they are fighting, so there are overlaps of signals that create some contention that will consume some power too. So those are added up into static power. Just some review, and then
Okay,
switching. Oh
may
yeah,
I add a comment?
yeah.
Yes, I want to go back to the leakage current, and this is very important in circuit design. That
Yeah.
the leakage current is proportional, or actually proportional with the temperature. So when the temperature increase or at a higher temperature, the leakage current is goes up very very high, especially for the latest and greater technology node, like 22 nanometer, 10 nanometer, 5 nanometer. The leakage current is very, very high. And sometimes we had a leakage current at a high temperature, even higher than dynamic current. So when we design, we
Yeah.
have to take that into account, especially for the chip that target like automotive or industrial, which had to work at like 125 C junction temperature. The leakage current very high. So make sure that our circuits or our power grid had to account for that power voltage at a high temperature.
Yeah, very good point. So thank you, Vu. So I want to add to that, right? So leakage power is the most important thing in wireless. If you have iPhone, you have a cellular phone. This is the guy that drain your current, drain your battery. So the challenge in designing SoC for cellular phone application, wireless application is not speed, but is static power. And as you go lower and lower, more advanced technologies, the leakage you become exponentially higher, and managing leakage is very, very difficult. And on the temperature side, there's something called temperature inversion, where at minus 40 degrees, you have more leakage current than the high temp. So there's a lot of things. As we go more advanced in IC design, leakage current is one of the things that we have to worry about a lot and do optimization for. Thank you, Vu. So now on switching power, right? Switching power. So this is this example of a circuit that we can take a look to understand switching power. So you say switching power is 1/T, the integral of IDD VDD dt. Right? So but as you can see in a circuit that you have a switching frequency, that becomes CVDD square of the switching frequency. What it says is that the switching power is increases when you increases operating speed. So that's something that that's a review. And short circuit current, like I said, there's an inverter here. If there's a P and an tree is when you have a slow rise and fall time, then the time that is in between, there are short circuit current flow from N to P. So usually it's about less than 10% of the dynamic power. And we don't pay attention to them, but sometimes, sharpening of the inputs will help with the power, even though it will increase the other part of the dynamic power, but something we don't have to worry about now. So, and the static power is really related to, over here, we already mentioned it, right? So it's consumed when the chip is in quiet mode, nothing happening, just only leakages, but no, so all the power, all the devices are off, but it's just leaking, right? So that's a quick review, actually. So that's a quick review of power. So we're not going to visit those things until later on, when we try to analyze the power grid for different electrical behavior. But we're going to go through this to understand how we build a power grid, without worrying too much about power and voltages and everything else. Just some layout thing here. So creating the power structure is called power distribution structure. So you pretty much have the power from the pads, and you want to distribute the power to the standard cells to the macros. So what do you do? And sometimes as a note, for simplicity, you're not going to see more than one voltage in the core in all the test cases that you are playing in the lab, but in reality, for SoC, you have multiple VDDs and multiple grounds, sometimes in the chip. So just a note there. So in this case, we only have just one for the core. We call them VDD VSS. Sometimes they call VDD core VCC, whatever. But in our documents, we call them VDD and VSS. without anything, we mean the core voltages. But there are also VDD and VSS on the IOs. As you know, the IOs have different voltages, and they're very strong, noisy, and very uh, um, uh, uh, they can interfere with a lot of stuff if we're not careful. So you have on here like one VDD IO and one VDD core, and you have VSS and IO and VSS core. So you want to create so the step in creating the power distribution structure is that you create the power and ground net. So in synthesis, you don't have those nets in the net list, but in the physical world, you need to have a net for VD, a net for ground for the core. So you create the net in the logical view, and then you connect them in the physical view, right? And so in the physical, you have two types. Basically, one is called rings. So ring is something that encloses like a closed loop here. So it's a ring either from the core. You remember this. There's an IO area, and then there's a core area that encompasses everything other than the IO paths. And then the macros in here. So the rings either around the core area or around a macro, or all the macros. And then you have what we call straps. Straps are lines that are either vertical or horizontal that sometimes you call them stripes. So you use those thick straps to distribute power to the standard cells. We'll go into more details on that, but basically that is a creation of the power distribution structure, and exactly how we do it, we'll go over it a little bit more detail. So first of all, power net connection. Power net connections, like I said, is not in the synthesized net list. So we create a net, and then we need to have a logical net in order to do any operations. So now and then you will create. You want to create. You want to connect them. But first of all, let's go through some terminology. So in here, assuming that you have VDDs and VSS going from off chip, so you have we call paths, right? So just terminology. So all these VDDs, red are VDD paths. And then VSS in green, in blue, they call VSS paths. Those are paths. And then you have rings, right? The rings is around the core. This is a core ring because the core area is in here. And then you have standard cells. These VDD VSS, you call them pins, right? The paths here and the pins here and the rings here. And then you have a memory or macro. Typically, you either have straps like this as VDD and VSS pin, or sometimes you have in your lab, you will see you have rings inside already of VDD and VSS, so people can connect the power to the ring, and then internally they will distribute the power. So these are called pins as well. And then you create a code, you connect them using maybe these animations of order. And then you have nets. So we create a VDD net and we create a VSS net. When you create in logical, you don't have this physical anymore, and then you run some command to route them, then you have physical. Okay. And then right over here, so you can connect the VDDs and VSS pins of the memories to the net. Therefore, you connect to the ring, or you create the ring and you connect them to the net. Therefore, you connect them to the path. They are when they are on the same logical net, the router will connect them automatically. You just need to define them. So this like I said, sometimes you will route over top of the memories and veer down on these internal power grids, or sometimes you just route to the a ring. So you connect logical nets by connect global uses this command connect global net. This specific to Cadence tool. And oops, sorry.
Until before you move on, may I ask a
Yeah,
question? Yes,
yeah,
I think it's helpful for the student.
yeah.
Will you explain why the power and ground paths were placed where they are?
Okay. Yeah, so this is the the perfect example of you have power and ground everywhere, right? But sometimes you don't have the luxury to have more than a pair, for example. But you're talking about the paths, right, Vu?
Yes, the path, the
Yeah.
number of paths, but the number
Yeah.
of power and ground paths and their location
Right. So their
in the
location.
pathway.
So yeah. So it has a lot of thing to do with the best location for IR drops. Maybe we'll have some other additional information, and maybe related to board that I don't know. But but ideally, the things that is in question here, it will be the IR drop. As you know, we will have to minimize IR drop. So if you have here the location, the distance between this and any internal places in the on the chip, you have you are close to either of these pairs of paths. Maybe it has something to do with also the board design. Will you want to add to it?
No, that is the point that important. That is the I graph that you distribute them spread them out. So anywhere in the logic that any cell can also get and draw the power, and get from as close to the source as possible. The source here mean the power supply pad or pin.
Yeah. So the closer you are to the path, the small IR drop. If you have small IR drop, you can tell it's better for your speed and sometimes power as well. So okay, that's good. And in addition to the standard cells, right, you need to connect and to standard cell and macro power and ground. You also connect something called tie cell. Tie cell is something that you need to understand because it's an important part of the physical design. So tie cells are the cells that we use to represent a constant zero or constant one, right? So as you know, in digital circuit, constant one is a VDD. So if you have a gate inverter and you want to tie that gate to one or zero in your logic, right? You would normally just connect them to VDD or to ground. But the problem is that the input, there's a gate here. The gate oxide is very thin. Any voltage surge on the gate oxide can damage the gate oxide. So that's two things that can happen during fabrication due to antenna effect that you will need to learn later. There will be voltage surge when you put down the last layer of metal on your chip, and that voltage surge, if it will go directly to this gate, it will rupture the gate. So we don't put tie this one to VD directly. We use a tie cell instead. The tie cells are created in such a way. This is a tie high, means that if you always need to be one, it will be connected something called we call it diode connected, where VD and VG are connected together. So VD connects to VG connected together. As you remember the transistor theory, that VDS equals VGS. over here, VDS equal to VGS. So therefore, VDS is higher than VGS minus VT. If you look at the transfer curve, that means that the transistor here is in saturation. So that means that this guy, when you look at here, then this node always at 0. So if this is always at 0, then it will turn this gate on always on. So out is always at VDD. So out is still 1 like this. But now the VDD is touching not the gate, but touching the diffusion here. So the diffusion here is much more is better. It won't be rupture. It have breakdown voltages and everything, but it's a lot higher than the gate. So this is how you do it. Likewise on the tie low is just the reverse. So the P here that put a 1 here all the time. So this one always a 0. So that's something to understand. So in the gate netlist coming in from synthesis, you only have 0 and 1s. You don't have tie cells, and then you will, in the physical world, you will insert them, and it's automated, but you have to specify them. And feel free to interrupt me with questions. I love questions. Please raise your hand or type questions, and Boo and Dave and Bart can tell me. But I would prefer to have questions during this. Oops. Keep on hitting.
So Phil, we did have one question come in. Does using tie cells cause any bad effect on the circuit?
Tie cell bad effect on the circuit? No, absolutely not. You would imagine that, yeah, it is inserted and it sits there and doesn't do anything, right? So because this is a constant, so there's no timing going through it. So I sit there and just do that. It has no. I'm not aware of any negative effect on it. Does But and Boo, do you guys know if there's any negative effect on it?
No, then it took up some space, right?
Yes.
Yeah. Okay. Yeah. So it's a must. If you don't have it, your chip will not be yeah.
Yeah, I
reliable.
mean the tie cells is very important. Starting at about 130 nanometer design below. You know, at a bigger geometry is you know, not a must, but at 130 below, you gotta have it.
Yeah. Okay. So
And Phil, the next question to come in is the inverter could have input logic 1 or 0. So how do we determine which tie cells we need to connect to inverter?
okay. Yeah. Thank you. So it is logic, right? So so when you, but it just comes, so your logic, right? Your logic design calls for a 0 or 1, right? So it's just already predetermined, because sometimes you want, due to digital logic, sometimes you don't, you have to have a 1 or a 0 on a particular gate, because you want to drive it, you want to control that. So yeah, that's the answer is coming from the input netlist. Okay, and so that's power net connection. So now, how do you build the different things, starting with a ring, right? So a ring, like I said, 2 rings, core rings and macro rings, right? Or block rings. So they call block. A block really is just a macro or custom cell. They call it just a block, meaning a cell, but bigger than standard cell. We call it a block. So you use a command add rings, right? To do that, and you, before you put a command add ring, you want to tell what kind of ring you're adding. By the way, thank you for the questions, right? So no question is you ask question doesn't mean you don't know. You ask question. Don't worry about asking stupid questions or asking trivial questions. Yeah. Okay, which case of VDD of IO path is lower than the core VDD? Good question. This is really this is so typically it's higher because you can see, you know, internally you have low voltages, right? Because you want to be as low power as possible, but sometimes you need more VDD to meet the speed. But the outside is a physical world, right? Physical world usually it require because of the sheer size of the board, whatever it needs to drive. Usually the IOs are higher voltages on the outside of a typical SoC. For specific SoC, maybe some analog SoC or anything like that. I don't know. It's possible that I haven't worked on any IC that have lower I/O voltages. But there are in the past there are some TTL logic that was 0.8 volt, right? So you interface to the very old TTL logic. By the time maybe you have to be your IOs are higher, lower than your internal voltage, maybe that by the time 1.5 volts, whatever. But in modern ones, I haven't seen it. Yeah, good question.
So I can add a comment there, and few. So
Yeah.
the question is, in which case the VDD of the IO pad is lower than the VDD core. So today, for 22 nanometer or lower, the typical operating voltage is between 0.5 to maybe 0.9 volt. And for the IO pad, in the past, the IO pad was like 1.8, 3.3, 2.5 volt. Now it's moving down to 1.0 volt. That's a typical LV-CMOS IO pad. But for the IO pad, a special interface like DDR for the interface to external DRAM, because this IO pad can operate at very high frequency, like 2.4 gigahertz or higher. So the voltage have a significant contribution to the overall power consumption of the IO pad, and so the power consumption of the system. So the new type IO pad like LPDDR4X, LPDDR4 is 1.1 volt nominal, but LPDDR4X is 0.6. So that's just one of the example. You have the IO is lower than the VDD core in some case. There also another type IO called the LVDS, stand for low voltage differential signaling. It's basically a pair of IO, and it's a switch at very low voltage between 0 to 0.5 volt. But the supply to the pad is actually at higher voltage, typically 1.8 volt. But the signal only switch between 0 to 0 volt to 0.3 volt. So those are two examples of the IO pad that have the lower voltage than the VDD core.
Very good. Thank you, Vũ. There's another question. At the core ring, is blue line ground below or above the red line VDD? Okay, that's a good question. So in here, it just represent the logical connections. So it doesn't mean this is a layer, right? This is just, hey, you know, for VDD, we mark it red, but this is not the layout. So in practice, you will see they can be at the same level, a layer. For example, in your lab, you see the horizontal VDD will be in metal 9, ground will be in metal 9 on the top and on the bottom. And vertically, you have metal 8 on VDD and metal 8 on ground. So they don't have to be, the layers have nothing to do with the logical representation here. So they can be on the same layers and depend on whether or not they go vertical or horizontal. So yeah, so I guess you asked about above, below, you mean the layers, right? So okay, so yeah, keep the question coming. Very good ones.
There's one more question of you.
Okay, which metal for power routing is it isolated between power domain? Very good. So you see, we typically use the highest metal simply because we want to have the low resistance. So when you go from the paths to distribute sometimes you have billions, 20 billions of transistors in a chip. So the you want you gonna see the IR drop is very important, but as you know, IR, right? So the resistance, to minimize the IR drop, you want to have the lowest resistance. So low resistance means thicker metals and higher metals. So on the main trunk, then you
Recording
want.
in progress.
Oh, you forgot to record.
My apologies. Thanks for the reminder.
Yeah, too much fun in Vietnam the last few days. You head out when?
I leave tomorrow morning. I'll be on a plane back to the States.
All right, all right. Well, okay, have a good trip back. Okay, so to answer questions. So you will use the highest level. In this lab, you have an AP, right? A layer, and then you have metal 9, metal. I'm not sure if we have AP in the lab, but basically the highest layer and highest layer usually is thick layer. So typically you have an ultra thick, and then you have a thick, and then what you have regular. So usually the routing inside the chip are really the regular metals, and the lowest metal 1, usually is a thin metal. So a lot of routing from metal 2 to metal 6, metal 8, whatever, are what we call regular metals. And then the higher level, you have a thicker one, you call thick metal, and then you have ultra thick metal, and you have the RDL redistribution layer, etc. So you want to use the as much as possible the higher layers first for RC, and then you will have to step down because metal 1 is used or metal 2 is used in center cells. So eventually you have to go all the way down to metal 1 or metal 2 to feed the standard cell with power. So you step up multiple grid before you go down. So the lower grid will be in the lower levels. But how about the size of VDD VSS usually is? Oh, another excellent question. You can see there will be a trade-off. So based on your power, we'll go over that. But based on the power analysis, you determine the width, right? Of course, if you want a higher lower resistance and you want to have thick, wider wires. But if you do too big of a wire, too wide of a wire, then you take away the routing resources. So while you have good IR drop, but you have no more room to route the chip, or unless you grow the die, therefore you grow the you increase the cost. So there are trade-offs that require you to be accurate to have enough for the constraints and to meeting the IR drop constraint, but not too much just to impact your cost and routability. Wow, excellent question. Yeah.
Yeah, that's a really good question. I just want to add to that on few that the side typically we would like to have the size of the VDD and VSS the same size at the IO pad. It make it easy to do the planning, and if needed, we can just add more pad, either more VDD and more VSS pads.
Yeah. So typically the highest layer is very thick, and you don't use them for routing purposes. Mainly, you use them to distribute the power. Yeah. Okay. All right. So going back to adding the ring. So we're talking about a ring here, right? A ring means like VDD and VSS around a core block or macro block. You see this enclosed, right? It's a continuous loop. So you want to tell the tool to say, hey, what is the top layer and what is the bottom layer? This have something to do with the fact that if you have metal 9 and you go over some structure, you say if you see a cross section connect all the way to metal 1, but you do a metal 4 here, then it will see a cross section of metal 1, it won't veer down. Right now maybe it doesn't make a lot of sense, but basically you have, when you have a route, you need to, when you intersect with another VDD underneath, then you want to veer down to make a connection. So this kind of control how deep you want to veer down. And then you want to have some veer controls by default, it will fill in the veers on all the overlaps, but sometimes you want to have less or more, and you can have these little control. So you set up all these control of what um, the ring looks like, the width, right? The pitch, the spacing in between them, and what layers on top and bottom, etc. You see more details on here that in later one. That really tell you exactly many different things that you can do to control the creation of this ring. Khánh Dương, is it possible if multi-voltage domains are routed on the same metal layers? Oh, absolutely, yes, as long as they are not shorted together. So yeah, they are different voltages, but they can be in the same layer, and as long as they don't touch each other, right? So creating a short. All right, very good. So now two types, block rings and core ring. Let's talk about core rings, right? So core ring, so you make sure that you don't select anything, and then by default it will build a ring around the core area. The core area you already defined, so it built outside of that core area. So in here you see this is called stack via top layer, metal 9 and metal 1. This is what I mentioned about controlling the veering down. If you have 4 here, then it won't veer down to metal 2, metal 3, metal 1 if the structure cross those layers. But in here we say, okay, veer, if you see metal 1, veer all the way down. So in here you say ring, right? Connect VDD and VSS net, right? And then layers, it said top, bottom, left, right, meaning what you gonna be covered on the top, right? So the ring is around this. The ring is around the core, right? So what layers you want to use the top? In here you say 9 and metal 9 on the bottom. And then you say left and right are metal 8. I mean metal 8 vertically, you create them in metal 8. And you can see here, metal 8 is used on both VDD and VSS. Metal 9 is used for both VDD and VSS. So two different nets, they don't touch each other. They can be on the same layer. And then there are different things like width. Yeah, each of these, in this case, I said, give me 5 micron for each of these. And then the spacing between 1.25 micron in between. So you play with this number and the power grid will be created after. And then the offset, just relatively where you start. So that's the detail. And you see here, all the vias are put in the overlapping, but you can have a control. So I want only 50% or whatever you want to control. So this is the creation of the core rings, and this shape will give an attribute. It's called core ring. So the attribute is used by the physical router for different purposes. I don't know. But basically, usually there's a physical shape and there's an attribute attached to that shape. So in this case, it's called coring. and that's for the core, and for the macro similarly, but now you have to select the blocks, meaning this is all these blocks, right? Sometimes you say, hey, this block already have a ring, I don't want to build a ring around it. So you select all the blocks by using this select object command. And when you select, and then you do like before, you see all these, you set db to set all the attributes, how the ring is built, like layer, spacing, etc., similarly to the core. And then you use a command called that ring add rings, and I forgot to mention is the type called block ring. If you see over here, I forgot to mention this is the type core ring, right? So you have block ring and core ring. And then it will build for each macro. It will build a ring around it, similarly to the core, right? It's space from the macro. This is VDD, this is VSS, and you can see the VDD and VSS. There's some smart sharing in between adjacent macros. But you use setDB to control the width, the spacing, etc., the viewers. And then you type a command. You see over here, it select all these memories. And when you hit a command, it build all these strings around it for you. Versus you have in the past, sometimes we have to do it manually by scripts. So, and then these type of rings, they put an attribute called block ring for future operations on these shapes. Yeah, so that's a block ring, right? So that's pretty much for creation of the rings, and then the creation of stripes. Stripes are, like I said, it's straps. It's just lines, right? You see here, these are the rings. These are probably the IO rings, internal IO rings. In this test case, you already have internal rings, and then you build on the ring outside of it. It's kind of overkill, but anyway, so in addition to the rings around the macros, for the standard cell, you usually build it's called stripes or straps. So you will use a setDB command to add to specify what kind of things you want to do, or what kind of stripes you want to add, and then you run the command called add stripes, and you do a dash layer. So over here, for example, we will still say you do metal 9 to metal 1 for via stacking, and then you do a net, you do a layer. So in here you set direction horizontal. So you are building, so underneath here are standard cells. So you say, I want to build the stripes of metal 9 horizontally, and I'm going to do each of them with a 5. A spacing between them is 10. It doesn't mean, it doesn't say this is a pair. So in between the two VD and VSS, spacing is 10, and set to set distance. Set means that this is a pair from here to the next set is 120, and then you start from the bottom here. So this is the core. So usually you start from the edge of the core and you start from the bottom. Means the first one will be offset 70 from the bottom. So this is how you do all these different numbers to specify exactly what you want to build. So this is horizontal metal 9, and then in addition you will build the vertical metal 8 in blue here, light blue here. So you use the since add stripe, direction vertical, layer metal 8, and width, whatever. So this is how you build the stripes. And these are the way you distribute the power to the standard cells. So the rings are the way to distribute power to the macros, right? And in a lot of times, we have we don't build rings, but we have power straps, like I mentioned, right? I show an example, and over here, right? A lot of time you have power straps like this, and then you run on top and you veer down on top of these pins. So you don't need a ring. So in some cases, to save areas, that's what you do. but it's really depend on your overall design. And I believe that is all I want to cover for today. And so in summary, a summary, you go through the step to create the floor planning database in preparation for the placement step. But like I said, there are more to Power Grid. We want to know what IR drops are, what EMs are, what kind of things we need to pay attention to, what kind of trade-offs we need to make in the creation of Power Grid. So we're going to cover them more on Friday. So look forward to more information that I prepared today. So we'll try to share with you as soon as we can. And then next week we'll be just wrapping up whatever else we need to cover for a complete floor plan. Before I hand over to Bud, who's going to cover he's going to be teaching the placement and CTS. And last but not least, Thuye will be teaching the routing step. So this is my last week. After this, I can go on vacation and relax. So yeah, we have 4 minutes before the break, or we can take a break now, or we can, if there's some question, we can ask now.
So we had one question come in. After power planning,
Okay.
how do we check the assertions for potential violations?
So I'm gonna cover that. I'm not sure what you mean by assertion, but we do have power grid analysis is the steps that we want to do to validate that the power grid doesn't have any EM violations, no maximum IR drop violations, no DRC, etc. There are steps that we need to make sure that we have high quality and clean floor plan before we actually do the placement. We'll cover in terms of the rules, the goals. So I do have a question. As I prepare for today, I have some information. Either I can go over the detailed technical now, or we can go over the labs and then go over the technical detail later. Actually, it's better to go over the labs, not too much information in one section. So yeah, we'll go over a little bit more. Can you tell me exactly what assertion means in your question? Kan or kan? Yeah. Or say yes if I did answer your question, so you don't have to.
So and Phil, let me add a little bit more. So at
power. Okay. Yeah.
Okay, yeah. So at this point, after floor planning, the only thing we're really concerned at this point is to make sure that the PG is short free. So that's one of the check that we're going to go over in placement. So
Awesome.
and
Awesome.
also the during the power analysis at RTL level, as far as specifying the width and how much power grid, that is already been done, right? So you build a grid according to your power specification, and then once you get to you place all the cells, you route everything, and then that's the final analysis will happen, and then with the EM and IR and so on. So it'd be more accurate once you route and everything, all your cell, all the cells added for fixing setup timing, hold timing, and things like that to be more accurate. So the final will be done after the design is already met timing around it.
Yeah, excellent. So in terms of power validation, exactly. So I'm gonna go cover that next Friday, right? On Friday, and like Bud was saying, yeah, it will be at this time. It will be what we call early power grid analysis. However, we still can validate different things, and with without the actual final circuitries, the methodology should be good enough for the tool to tell us that we are going to be good or not. And then if we in actual implementation, it could mean that we have to go back. So it's iteration process. If we might have to go back and do some fixing for power grid if your power turn out to be a lot more. So we'll go over that. Okay, so it's 5 o'clock, 10 o'clock. So let's take a 5-minute break, right, Dave? And then we can go back and do the, oh, okay, but we'll need to drop. All right, we'll see you guys back in 5 minutes and we can go over the labs. Hey, But are you still there?
Yes, I'm listening. Go ahead.
Hey, do you want to, maybe you're not prepared, right? But if you want to drive the lab, you can. Otherwise, I'll try to log in.
No, I haven't looked at Tang's lab.
Okay.
So
Okay, I'll log in.
Everyone will return to class in 1 minute. All right, everyone, welcome back to class. I think Phil is getting set up with the labs for the second half of today.
Okay, so let me share the screen. Okay, this is the cloud, and so I don't have the instruction set up, but basically okay, so you see Tien set it up so that we can run different steps. So you will be running import. And after import, you see this view, right? If you see a mobile view, then you see the macros and the logic, and then you place the instances. So you place the instances, then you'll go into the layout view, and you're going to see this view. So all the macros already placed. And over here, you want to turn off this annoying, it's called terminal here. So when you turn it off, you see this, what you want to see. Then you run the placement adjustment. This, you guys already went through this, so I'm not going to go through this anymore, but just to set up the stage. So after you run the that placement, you see this view. So everything is adjusted. The die size already what you wanted, and now you have a view. And I'm going to turn off the blockages. So now you have this view. So everything is there. So now you're gonna go add a power ring. Right? So you can tell I'm not as fancy as Tien in terms of getting all these files. But so you see in here, connect power net, right? Connect global net VDD, type PG pin, type high and low, right? So yeah, and then VDD, this pin-based name, meaning that the pin on the should I so these are VDD, right? You can, yeah. So what we're telling is that the name on the VDD and ground is those names, right? So you said base of VDD and base is VSS. And the net is VDD. So see this net is VDD, net VSS. So connect all these things to all the things that have the pin name. Connect this net to all the pins that have a VDD VSS. And then you connect the type low and type cell high to this net. So after you do this, you can tell there's nothing here because you only do this one as a logical connection. Right now let's turn on the pin. So when you do the pin object visible, That means that equivalent of you go in here and you do cell and you turn on the pin shape, right? On, off, right? Off, on. So pin shape here, you can tell that internally there's already a ring in. This is a pin on the macros. It means there's already an internal ring. But now you're gonna add to it. So I don't know why they're gonna do that, but that's what we're gonna do. So you're gonna add to it. You see in here, you say you're gonna add rings, and a lot of things are really I don't pay attention. So things that we pay attention is here, right? You say stack via top metal 9 metal 1, meaning that if I create something and it run over top of anything, above metal 1 and above, I'm going to veer down, right? And then go exact crossover side. I think crossover means, intersection. There's a lot of these things you can do a man, right? If you're curious, you can do in here. 10 probably already told you, right? You can do a man here. And then you can say, hey, this is an attribute, but you can still do a man on the attribute, and then it will tell you exactly what it is. But for the sake of time, we're not going to worry about that. But this is a command add ring, right? So we do the setup, and then you add ring. So let's talk about that ring. You see here, you find that the net, there's an empty in the net. So I guess this one will create some errors. I think it's intentional, but let's see if it does that. See, it's invalid net names because there's nothing you put in here. So what you do is that you run the next one, which has a right. Hello. Okay, so next one you do it again, and then you give it this net name VDD VSS. You see here. So so you're gonna run again and see what happens. So now it's not clear, but you can see here the ring has been added. But if I turn off the pin shape, it's obvious. Right? So there's no, you do a full, you see this ring is added around the core, right? So the ring, like you want metal 8 left and right, metal 9, right? So this is metal 8, right? If you do a Q, hello, then you see it's metal 8 right here, and it's connected to VSS, right? So it's over here. So it does what you need it to do. So you can play with this and play with the numbers to see how it's built. So basically, you see where where these little these are the rows, right? This is the core. This is the edge of the core. It builds off this one and with an offset and a distance and a width, right? And over here should have all the vias. Yeah, you see this one is all the vias in it. So that's the coring, and then next what it does is I think I did it too. So I did the coring, and then the next one we do the block. So first of all, you need to make sure only the selection of the blocks that you want. So first of all, you should deselect in case you click on an IO cell somewhere. So to be safe, you want to deselect it all, and then you select is memory is black box. So meaning that all the macros, right? If there's a black box here, you want to select them too. So you're going to build a ring around each of that. So so now you can see they are selected. Okay, forget about the flight line. But over here, you set up like metal 9 to metal 1, crossover similarly to that. But in here, you see, I forgot to mention again, block rings. So over here, you say type core rings. Over here, you type block rings, right? And then you say top metal 9, left, right, metal 8, similarly to the core. And the width, top, you can do one for all, or you can be specific for top, bottom, what width you want, left, right, and offset, and different controls. So this one you're gonna just build the block rings. Right. So you build that block ring, as you can see over here. You see now you have this. Let's go over here. Now you see the ring around each block, right? Like I mentioned, sometimes it just smartly, share them, right? So that, and yeah, over here, yeah, they share. But if you turn on the pin shape, you can see internally it already have a ring. So it's kind of an overkill. Maybe it's not. Maybe it's still good to have a main ring here and then connect to the sub ring, because you go. Yeah. Oh, wrong way. Yeah, you see. It's just like routing of đi thủy lợi or whatever. You want to distribute water here, then you have the main feed, and then you distribute the juice over. So if there are questions, please ask me, because I think this is so simple that we probably finish with the lab very fast. And then there's another add ring, block ring around selected. I don't know why we have this similar thing. What does this one do? I don't know. I didn't pay attention to this one. See what it does. Oh, I see. I don't know. Error, right? So it's just meant to be say, if you don't do it right, it will be error out. So that's building the ring, right? So so it's very straightforward. And then let's build the stripes, right? So okay. So what does it do? So add a power stripes. You can see here it will be metal 9 horizontal, and then width and every of the details, like with spacing and everything. And with the set DB first, and then add stripe later, and see what it does. So now you can see the horizontal stripes. And let's turn off this pin shape. So you see horizontal in metal 9 being built. Right, so it's just horizontal. So it did connect to whatever, you see when the metal 9 is connected, it's C metal 8 here, so it just connect already. See VSS connect to VSS, VDD connected to VDD. So it see the pins here, even in the pin. It see the pins here, and pin here is a different layer. It may be metal 2. So if we are down from metal 9 to metal 2, so so that's what this strip, horizontal does. The horizontal stripes, and then and we have the next one. What does it do? Yeah. So next one is say do metal 8 for me vertical, right? And with all the width and spacing, etc. So it does this. So pretty straightforward. But the important thing is that you need to understand what these are for. We're going to analyze them, why they're needed and all. So metal 8 here. So you can see metal 8 is built vertically. So some of them already there in the ring. Now you have metal 8 go. And then you see whenever metal 8 cross metal 9, it veers to the metal 9, right? So metal 8 just added. But if VSS is see a cross section VSS, it just put veers in here. Right, you see veers. So and then try to see if we have over here we don't see the standard cell yet. And then you write the DB. I don't know if this is needed or not, but so that's a stripes or straps, right? Vertical, horizontal. You can see they build in pair, right? So now in the standard cell area, you have this grid. Right, you have this grid, and Friday you see how this grid is represented in terms of resistance and current taps, and how they are analyzed, and the IR drop to all these different locations, how they analyze and making sure that they meet all the requirements. So that's the grid. This stripes mainly is for the standard cell area. Right, it's a regular grid. And then you do S route, special route. So what is it? So in here you see we didn't cover it yet, but basically it's a command called route special. Is a special router. It's not the placement router, but say connect all the block pin, pad pin, and core pins together. So I guess the attribute that they put on when we have the cover, so it's used here. It's used in this size. The block pin, core pin, and pad connecting together and have metal and 1 to metal 9. So the 2 nets and block pin use left, all these different controls that I didn't go through, but basically what this does is going to route. So you build the straps, you build the rings. Hello, it's not responding. Okay, then now you run the route. So let's see what it does. Right? You see, right over here, it has some additional shapes that the router just build these shape in metal 3. And this is so metal 4 in yellow, and this is VSS. You see VSS. So they go here and then they go here, VSS. So you see pad VSS. Let me just zoom in here. So a ton of VDD, pad VSS 8, VSS 7, VSS 6. So it route from the ring, right? It have a special router to route the pad pin. Over here you see it said route the block pin, pad pin, and core pin together. So this is core pins, right? The shape it at is at an attribute called core pin, and then the round, the ring around the macros is called block pins, and then pad, all these pad pins. So they just see the logical connections, and now they do all these shapes. So all these VSS connected to pad from the rings, right? And so it looks like all the pound and ground. So you see VDD here connected to VDD. And it looks like it only needed to connect from the outside. Oh, maybe it did some of these, or maybe it did not. No, these are middle 9 already added already. So it looks like it's from the pad, it connect to the outer ring, the core ring, and everything is connected. So I think that's it for this this lab. I think that's all Tien has. Any question? Straightforward. So the important thing is understand the theory, and the lab should be straightforward. So at this point, we have half an hour. We're gonna go over the pre-assessment to see if anything else we need to address. So I'm going to kill this guy. So let's go over the assessment. We'll go over this assessment first, and then we'll go over the. Oh, I remember I owe someone a question of what determined the core. So let's see. Someone asked a question. There's a core of the other. Maybe I just use. I just use this one. So there was a question about the core to IO, right? Spacing. There's a core to IO spacing, and what determines that? And so, but I checked with the DRC LVS guy here. Apparently, it's not on top of their head either. It's just something, if it pops up, you know what rule is violating. But since it is, it appears that it is determined by when you build this power ring, you need to have a minimum space between the core and the IO. So by the fact that you have a requirement on power ring, then that space is probably cover all the design rules. So it's not on top of our head in terms of what determine that space. So most likely it's going to be just the core ring itself. But I'm still trying to get the answer from our DRC LVS at Skyworks and let you know what they found out. So let's see. So let's go over the reassessment. So we have 66 responses, and you can see the difference. So why is establishing a power grid essential? So let me see what the responses are. That's actually only 12 got correct. And so to it, but maybe you guys can after we're done with the lecture, see if the response is better this time. So I don't want to do the poll. Maybe people just answer question A, B, C, D in here. Why is establishing a power grid essential? A, to distribute power to all cells on chip. B, to ensure signal integrity. C, to ensure reliable chip operations in all conditions. D, all of the above. Maybe just type in the chat to see what you think the answer now is. Just curiosity. Or actually, maybe someone can help me just put a poll on all these things, and we can have fun, interacted. Anybody? Oh well, the answer is to distribute all power. Huh. I think this is wrong. This should be all of the above. I apologize. Yeah, I think Lê Thanh Trung, all of the above. This is inaccurate. Yeah, the answer is no wonder only 12 got it right. Okay, all right. Apology. Yeah, it's all of the above. Okay, so the answer is all of the above. All right. So keep on typing. What is the relationship between VDD on I/O paths and core VDD? Right. A, VDD on I/O paths is always lower than core VDD. B, always higher. C, can be either higher or lower depending on the design. And D, VDD on I/O paths is unrelated to core VDD. This is not a very good answer, but please type in what you want, what you think, A, B, or C, or D. Just don't pick D. This is not very good answer either. So you can tell these are done in a rush. Nguyễn Đoàn Hoàng Phúc said B, always higher. B, always higher. C, Lê Thanh Trung, C is correct because we already have some question, right? So I would think B is a good guess, but like Vũ was saying, sometimes, VDD on I/O path can be lower. So yeah, either B or C are acceptable answers. Okay, thank you for the answers. How does the choice of metal layers in the power grid influence electromigration in VLSI design? Right, the choice of metal layer. Oops, sorry. Sorry. What did I do? I reviewed the correct answer already. Yeah. A, metal layer selection has no impact on EM. B, thicker metal layers exacerbate electromigration risks. C, thinner metal layers increase susceptibility to electromigration. And D, proper metal layer choice can help mitigate electromigration concerns. What is the answer? Yeah, thank you, Nguyễn Nam Hải, Đặng Vinh Quang, Phan Trọng Nhân. Yeah, the answer is D. Okay. Thanks all for the answer. What is the primary purpose of a core ring in VLSI design? Enclosing specific functional blocks, providing localized power distribution within the core, surrounding the entire core to ensure uniform power delivery, minimizing crosstalk between neighboring circuits. All right. The correct answer is C. Yep. And I don't know this will be useful or I have to explain. I think the request to go over this is probably because I didn't release the test result. When I release the score, then you see what the correct answer is. So I don't. So if we go over this and you need more explanation, then let me know. Otherwise, we just play the game again. Yeah, after you sit through the lecture. Maybe what is the primary purpose of a block power ring in VLSI design? A block power ring enclosing the entire core, minimizing voltage drop, ensuring stable power delivery within a specific functional block, enhancing clock distribution efficiency, providing flexibility in power distribution without focusing on circuit blocks. So the answer is B. Enclosing the entire core, no, we only should block, right? Minimizing voltage drop and within a specific functional block, sound good. It had nothing to do with clock distribution for sure, and it has to be around a block. It's not cannot be just regular flexibility. So yeah, the answer is B. Oh, thank you. A lot of you guys got it right. All right, is a block power ring always necessary? True, false. Enhancing clock distribution, providing that flexibility without focusing on the circuit block. Is it always necessary? True or false? B, false, right? Yeah, because that's correct. Because sometimes you already have a ring around, or sometimes you have the yeah. Is that this guy? Yeah. Yeah, sometimes you have a strap, then you just hook directly to the straps, and sometimes you already have a ring, you can connect to the ring without building the ring. So, okay, good. I think all of you got that answer. What components are typically connected to the core VDD? Only flip-flops and latches, ALUs exclusively. Core VDD is not connected to any specific components. Standard cells, flip-flops, registers, memory cells, and clock tree networks, among others. Awesome. D, yes. Correct answer is D. Why can't the core of a VLSI chip use the I/O VDD? The core requires higher voltage. The core is less sensitive to noise and interference. The I/O VDD is optimized for mixed signal interface. The core and I/O sections have distinct functions and voltage requirements. Yeah, a lot of you answer D. That's correct, right? No need to explain that, right? Because not always the core doesn't always have higher voltage levels. The core is not always less sensitive. I/O is optimized for mixed signals. Make no sense. Okay, what can the core of a VLSI chip use I/O VDD? Oh, is that a repetition? Sorry. Which design consideration is crucial for managing IR drops for dynamic circuit switching? Clock trees, optimization, power grid density, via placement, decoupling capacitor sizing.
So this one is not easy to answer. Let me see. Did somebody say D or? Okay. Right. So the answer is decoupling capacitor sizing. So it's very good answer for it, but we didn't go over that yet. So so basically, dynamic circuit switching, you as we already went through that. Let's review that. I don't think we went over it. So I'm going to go over that next week, but maybe I can. Never mind. I'll go over it on Friday. Yeah, but yeah, basically the decoupling caps will play a very important role in terms of handling dynamic power issues. And okay, any question before maybe we can go over the lecture 6 question answer. I don't know if this is useful or not. You guys tell me. Any comments on the usefulness of going over the assessment? Oh, it's very helpful. Okay, I'm glad. Okay, so let's continue then. Let's see if the where's lesson 6. Maybe we go in lecture 6 pre-assessment. Yeah, you can tell these things which it, but in maybe in future classes we'll be more prepared. So the flipped classroom is really something we came up the last minute, so we still try and error. So we just come up with this, in a very quickly manner. And in here there are 67, so it's good. Let's see what the distribution of the score is. Oh, sorry, we didn't mean to. Just we don't want to share the individual. So in here, yeah, most people got it right. So let's go through the questions. What are the main purposes of macro placement steps? Minimizing the total wire length, minimizing the length of the timing critical paths, optimizing area utilization, all of the above. Okay, cool. All right, D is above, is a correct answer. So all of the above, because minimizing total wire length, right? The macro placement, the smaller when you do, you want to do for sure A. So a lot of people got A, a few got A too, but minimizing the length of timing critical paths, you can see, yeah, see, maybe it's helpful to get the So maybe it's a refresh since we have time. So minimizing the the wide length, right? The length of timing critical path. We mentioned something about a DSP circuit. Hello. And here is an example, right? So this is just DFT is really timing critical, meaning in a DSP chip, that's the critical timing critical path. So you want all the blocks to be close together, including the arithmetic units over here. So when you have the signal doesn't have to travel far. I mean, it can be reduce the delays. So absolutely, that's part of the floor planning. So placement of these things affects the timing critical paths. So optimizing area utilization for sure, because if you look at the standard cell areas over here, so by placing these macros, give a contiguous standard cell placement area. This is more efficient than you have fragmented and you see these notches. So these things is you can still route and you still can place, but the efficiency of it is not as good as this wide big standard cell area. So that's yep. That's optimizing area utilization. So yes, it's all of the above. What does macro placement contribute to time enclosure? No impact. It helps to improve the constraints. It minimizes the length of timing critical paths. It only affects area utilization. What is the answer? Say yes, Nguyễn Văn Duyên. Yes. Say yes. Say is correct answer. So there's no, because it does have impact on time enclosure. It doesn't help with improving the constraints. The constraints have nothing to do with the macro placement. Minimizing the length of timing critical paths, we just went through it, and it only affects area utilization. Area utilization only one of them, but it has more. So that's good. Thank you for all the answers. How does macro placement contribute to power distribution in VLSI design? Right. By improving the speed, by optimizing the signal paths, by placing higher power macros closer to the power source, by fixing the right design rules. Yeah. So right. Improving is not it help improve the speed, but it doesn't. It's not related to power distribution. Help with optimizing signal path. Yeah, the correct answer is C. Yeah. Yeah, because by placing the high power near the power source, that means it's power hungry. Related to IR drop as well, right? So do we have a picture for that? So basically, if the higher power macros draw a lot of currents, right? So it will have impact on the IR drop along the way. So the closer it is, the less IR drop and the less impact on the send routing logic. What role does macro placement play in achieving a compact design? It has no impact. It improves hierarchical organization. It optimizes area utilization. It increases the chip operating frequency. So this should be an easy answer. Okay. So, yep, the answer is C. What impact can longer buses have on the signal propagation delays? Increase the delay, decrease the delay, no impact on delays, introducing clock skews. Yeah, increase the delay. Right. All right. How does minimizing wire length contribute to overall chip performance? Reduce signal integrity, increases signal propagation delays, improve performance by reducing delays, enhance clock skew. Yeah, the answer is improve performance. So it's C, not A, because minimizing wire length that reduce the delay. So the RC delays. What is the one benefit minimizing wire length of frequently switching buses? Longer clock skew, reduced power consumption, higher clock crosstalk issues, increased signal degradation. Yep, the correct answer is B, right? Reduce power consumption, because when you switch the bus very often, so the longer the bus, the more RC, so the more power. So if you want to save power by making those buses shorter at the expense of some other buses, then you still gain because these buses switch more often than other buses. So you wanna give that priority. So how does reducing bus length contribute to low power consumption? It increases the dynamic power, raise clock skews, decrease wire capacitance, boost signal propagation delays. Yep, the answer is C, decrease wire capacitance. Right. So it has nothing to do with clock skew. It does reduce the dynamic power, not increase, or it doesn't increase the propagation delay. In floor planning, what is a chimney referring to? A narrow placement area between macros, area with excessive signal propagation delays, region with elevated power consumption, space intentionally left empty. Yep. Yep, the correct answer is A. Not C. C, the region with elevated power consumption. No, it doesn't always mean like it's it just look like a car, right? So it's a narrow in between macros.
Phil, we
What
had a
issue?
question. We
Yeah,
had a
yeah.
question come in. Do all signal paths in the chip use bus configuration?
No, was a bus only, mainly the data paths, like a program bus that holds the entire instruction, like 32-bit, 64-bit instructions, or a lot of time our data paths, like 32-bit, 64-bit data. But there are a lot of random logic that really have it's just single signals. Not all of them come in bus form. Okay. What issue is commonly associated with narrow placement areas? So increased wire capacitance, congestion and routing difficulty, reduced clock skew, improve signal propagation delays. It's an narrow placement area. Yep, the answer is B, congestion and routing difficulties, right? You see here, you have pins and you have signals coming in, you have hard time with congestion and routing. Yeah, doesn't have anything to clock skews, increase wire capacitance, I'm not sure. Improve signal, for sure it's not going to improve the signal propagation delay. What is the purpose of avoiding chimneys in macro placement? Decrease wire length, minimize clock skew, optimize signal paths, prevent congestion and timing issue. Yep, correct. Prevent congestion and timing issue. So it's obvious, right? That's good. Why are notches discouraged in VLSI floor planning? So notches are these guys, right? Notches. So to increase signal degradation, to introduce clock skews, to minimize wire length, to maintain uniform wire density and prevent timing issues. Yep, wire density, right? Uniform wire density and prevent timing issue. Why is a wire density? Right, so for notches like this, right? So over here, so wires are determined by the standard cell area. Over here, now all of a sudden you have signals that need to escape from the memories, in addition to the signals in the standard cell areas. So all of a sudden, wire density over here is more than wire density over here. So that's when you become, like cells have to be pushed out and critical paths are affected and congestions are here because you have more wires per unit area here. So you want to discourage that. It still can be routable, but it will affect your overall quality. How does the placement of macros impact the standard cell placement areas? It has no impact. It helps increase standard cell density. It can create congestion and limit available space for standard cells. It improves signal propagation delays in standard cell area. So what is the answer? Yep. Yep, the answer is C. It can create congestion, like we were mentioned, right? It notches and also the areas here. Yeah, if you don't leave enough space for all these I/O to escape, it will create some congestion problems. And so that's easy to understand. Why my moving macros to the edges? Oh, we're running out of time. Oh, well, a lot more. Okay, I think we run out of time, so I hope that is useful, and I didn't realize that we have a lot more here. So, okay, well, out of respect to people have to make the next class. Thank you very much for all the questions and answers, and hope you have a good day.